Okay, so welcome everyone to the Combinatorics Physics and Probability Seminar Series at Harvard CMSA. So we're very happy today to have Anna Seigal from Harvard University, the Math Department, talking about the invariant theory of maximum likelihood estimations with connection with polytopes and Torus orbits. And also recently they've been also connected with scattering amplitudes, but other people did this work. Yeah, so feel free to start.
All right. Yeah. Hi, everyone. Thanks a lot for coming today. And thanks, Matteo, for the invitation and for the introduction. It's great to be here. So today I'm going to be talking about invariant theory for maximum likelihood estimation. So this is a topic that I've been working on in the past few years. And today I'll be talking about joint work with my wonderful collaborators, Carlos Améndola, Kathlén Kohn, and Philipp Reichenbach. All right, as a general overview of what I will be talking about today, there are three main themes or families of objects and definitions and stuff that we'll be interested in. So there's the statistical side, and the invariant theory side, and I'll be focused on discussing these connections that we've uncovered between them. And in the setting that I'll talk about today, these relations arise via polytopes. So by connecting statistics to polytopes and by connecting invariant theory to polytopes. Which are both in their own right quite established connections existing. So you could say that the contribution of our project was to invoke the transitivity of the arrows in this diagram and to recall this one and recall this one and hence establish that one. But maybe that's not quite doing us justice, but that's the overall arc of what I'll be talking about today. So, okay, so this is the combinatorics, physics, and probability seminar. Okay, so we've got statistics, that's like probability. We've got combinatorics, so that's like, then we've got polytopes, that's like combinatorics, and then, so, okay, invariant theory, that will have to be what we have in place of physics. Okay, all right. So what I am talking about may be quite new and unfamiliar in terms of the setting that I'm describing, but I'll try to make it quite concrete, or I have already tried to make it quite concrete. So here's an example of something that we'll see later. So here's some quite concrete polytopes, in this case 4 copies of a particular polytope given by the convex hull of this A1, A2, A3, and A4 vectors. So this is the same polytope and various properties of this polytope with respect to point contained in the polytope. So, okay, this is to convey that hopefully the talk will be quite down to earth and understandable. Yeah, please stop me at any point if you have any questions about anything. Yeah, I also don't have too many slides, as you can see at the bottom, so I'm happy to go at an easy pace and to be interrupted. Okay, all right, so I will begin by talking about this arrow here. So what is this connection that I'm talking about between statistics and polytopes? Okay, so polytopes and statistics, a first example. So I'm going to be here discussing the independence model on 2 binary random variables. Okay, so the independence model is characterized by this multiplicative property on the probabilities. So the independence model says that if we have 2 random variables, x1 and x2, then their joint probability, so the probability that x1 takes the value I and x2 takes the value j, can just be obtained by multiplying the individual probabilities. So by taking the probability that x1 is equal to I and multiplying it by the probability that x2 is equal to j. All right, and then if we restrict ourselves to binary random variables, so each of x1 and x2 can take just 2 states, then we get a probability mass function for their joint distribution, which is just a 2x2 matrix. So here I and j take values 0 and 1. So this p0, 0 is the probability that x1 takes value 0, x2 takes value 0. So here's our probability mass function. And then the fact that we have independence means that this 2x2 matrix is rank 1. So that there exist parameters, which here I've called lambda 0, lambda 1, mu 0, and mu 1, such that each entry of the matrix looks like a product of 2 of these. So Pij is equal to lambda I mu j. All right, so that's our model. Okay, yeah, so as I said, it has a rank 1 probability mass function. So this means that the model can be defined implicitly by a single equation. So the determinant of P, this matrix of Pij's, has to equal 0. Okay, so here are 2 pictures of what this model looks like. So it lives inside the space of all possible 2x2 matrices that are probability mass functions. So that is 2x2 matrices of non-negative entries that sum up to 1. So such matrices parameterize the 3-dimensional probability simplex. So that's seen here from 2 different viewpoints. And then the model is the intersection of the determinant hypersurface with this probability simplex. So that gives our yellow model here. Okay, and the probability simplex is a polytope, but it's not the polytope that I'm going to be talking about here, but this is a polytope. So, okay, we have achieved our goal of connecting polytopes and statistics, but not yet in the way that I would like to. Okay, great. So now that we've defined this model, the next thing that we would like to do is, given some data, to find its best approximation on the model. So here's the cartoon picture, which looks quite a lot like this real picture. So we have our space that the probability mass functions are living in. We have our model, which is some subset of the space. And then we sample some data. So in this case, we would sample some 2x2 matrix of observed empirical probabilities. And we're looking to find the point on the model that best fits the observed data. So we search over the model and look for the point that's closest with respect to our prescribed notion of distance, and that will be our maximum likelihood estimate, or MLE. Okay, so this is what the data looks like. We'll call the data matrix U. So each entry Uij tells us the fraction of times that we observed the state I in the first random variable and j in the second random variable. So we'll just record these fractions. And then the function that we want to maximize to find the MLE is the likelihood function. So the product over all ij of Pij to the Uij. And since our model is parameterized in terms of these lambdas and mu's, we can rewrite this as an expression involving just the lambdas rather than the p's. And here the notation U0 plus means that we sum over the possible values for the second index. So this is the first row sum of this matrix. Okay, and then we can solve the equations that hold at a critical point of this likelihood function to find the maximum likelihood estimate, or MLE, in this case of the independence model. So it has this well-known formula. So our empirical guess for the parameter lambda 0 is the 0th row sum, and our guess for mu0 is the 0th column sum. Lambda 1 is the first row sum, and mu1 is the first column sum. Okay, so this type of model is very special, and it's a model for which you can actually write down what the maximum likelihood estimate is as a function of the data that you started with. So in this case, as a linear function of the data that you started with. But for more general models, this won't be possible, and finding the maximum likelihood estimate will be an optimization problem that you'll solve via some algorithmic approaches, via some iterative methods. Okay, so the MLE doesn't always exist. So we think of our statistical model as living on the strict interior of the probability simplex. So all of the entries of the matrix must be strictly positive. They can't be zeros. So what does it mean for each of these entries of our maximum likelihood estimate to be strictly positive? Okay, so u0 plus, u plus 0, u1 plus, and u plus 1 all have to be strictly positive. So this gives us a condition on the original data that we started with, our data u. So sufficient condition is that all the entries of u are strictly positive, but this is not necessary. So the MLE exists if our data u is in the relative interior of a certain polytope, namely this polytope here. So this tells us that u can be written as a combination of these 4 matrices with strictly positive coefficients, and this ensures that all of these entries of the maximum likelihood estimate will be strictly positive. So that's our condition for the MLE to exist. Okay, and this is the connection between statistics, specifically the existence of the maximum likelihood estimate, and polytopes. So a particular polytope that comes from the model and for which the existence of the maximum likelihood estimate is characterized by where the vector, where the data lies in relation to this polytope. So that's the connection between polytopes and statistics in this first example of the independence model. All right, maybe I'll pause here in case there's any questions. Okay, great. So, okay, what does this connection look like more generally? Well, in greater generality, we can consider a log linear model. So a log linear model is a set of distributions whose logarithm lies in a fixed linear space. Okay, so this is what our log linear model looks like. So it is determined by some matrix A, which is a matrix of integers. We assume that the all ones vector lies in the row span of this matrix. And then the log linear model corresponding to the matrix A is the set of all probability vectors for whom log of P lies in the row span of A. Okay, so let's see an example. So here we have a matrix A. I've sort of suggestively labeled its rows and columns, although I've done it with inconsistent indexing relative to the slide before, but I hope you'll forgive that. So here's a matrix A, and we can ask, what is the log linear model corresponding to this matrix? So if we consider the probability mass functions we get, whose logarithms lie in the row span of this matrix, what do they look like? Okay, well, we can check that log of Pij has to have this form. It has to be lambda I plus mu j. Okay, again, if you subtract 1 from these indices, so P00 is lambda 0 plus mu 0, P10 is lambda 1 plus mu 0, and so on. So the probability mass function P has to have this form. Its logarithm has this additive form, and that means that the original matrix P has a multiplicative form, so it's rank 1. All right, so this matrix A gives us the independence model on 2 binary random variables that we saw on the previous slide. Okay, and there's lots of other statistical models that are captured by different choices of matrix A. So there's big families of statistical models that are log linear models for a particular type of matrix. So graphical models, hierarchical models, and so on. Okay, and then as before, this is the setup that we're considering. So we have our model, it lies in some space. Now we have some data and we want to find the best, its best approximation on the model. And we're particularly interested in, does this best approximation exist or not? So is this closest point on the interior of the probability simplex, or is it on the boundary? Okay, so Birch's theorem gives us the conditions that characterize the maximum likelihood estimate. So it says that the MLE, given some data U, which as before will be some vector of observed counts. So this will be a point which we'll call P hat that lies in the model, such that applying the matrix A to the vector P hat gives the same as applying the matrix A to the vector U bar. Okay, so another slight notational inconsistency. So U bar is the relative frequencies that we were looking at on the previous slide. Okay, so the this is the equation that the MLE has to satisfy if it exists. And the statistical way to interpret this linear condition here is that the MLE matches sufficient statistics to the data. So we have our data vector A, our data vector U, we apply the matrix A to it, and this is the vector of sufficient statistics. So whatever our MLE is, we want it to match these sufficient statistics. And in the previous example, the sufficient statistics were the row sums and the column sums. But for a more general model, there'll be something else. All right, so let's define the polytope P of A to be the convex hull of the columns of our matrix A. Okay, so I'll let AI be the columns of A. So this is the same polytope that we were considering before for the independence model. We have these, these 4 columns. Then a theorem of Eriksson, Feinberg, Ronaldo, and Sullivan from 2006 says that the MLE given some data U exists in the model MA if and only if this vector of sufficient statistics is in the relative interior of this polytope. Right, so this is the generalization of our previous statement about the independence model to a general log linear model. So saying, how do we see if the MLE given some data U exists? Well, we just need to compute this polytope and look at the location of its sufficient statistics in relation to this polytope. All right. Yeah. Any questions? Okay, great. So now I'd like to move over to the more invariant theory side, starting with torus actions. So this is the group action I'll be talking about. So firstly, I'll define GTD to be the group of diagonal invertible D by D matrices. So these are just given by non-zero complex numbers on the diagonal. Okay, then the action of this group on complex, this should be M, not M minus 1, complex M-dimensional vector space is given by a matrix of integers together with linearization, so a vector of integers. So what does this action look like? Well, we have some element of our group, so a tuple of D non-zero complex numbers, and it acts on some point in Cm by multiplying that point by this diagonal matrix. So it's the diagonal matrix whose jth entry is theta to the aj minus b. So this is theta is a vector, aj is a vector, b is a vector. So this notation, vector to the vector, means take each coordinate of theta, raise it to the that coordinate of aj minus b, and multiply them together. All right, so this is our torus action. So here's an example. So this is the matrix A from the previous slide, and we can consider linearization 0. Then if we compute what all of these products are as we range over the columns of the matrix A, this is what we get. So we multiply the first entry by theta 1, theta 3. So theta 1, theta 3, not theta 2 or theta 4. Then the next entry we multiply by theta 2, theta 3. The third one multiplied by theta 1, theta 4, and then finally theta 2, theta 4. Okay, and b is 0, so we don't subtract anything from these exponents. Okay, so this is suggesting a certain connection between this torus action and a particular statistical model. So which model is parameterized by this torus action? Well, it's the same matrix A that we were considering on the previous slide, and we have this sort of multiplicative form of the entries of this diagonal. We can rearrange them into this 2 by 2 matrix form to see the connection more clearly. So if we start at the all ones vector and apply the matrices of this form for some theta to that all ones vector, we will parameterize the space of matrices that look like this. So this is the independence model. Okay, it's not really, because I started with the action on a complex vector space, and theta can also be complex. So it's really parameterizing the Zariski closure of the independence model rather than the part that's on the interior of the simplex, but it's pointing out a close connection, which I'll build on a bit later, between this this particular torus action and the corresponding statistical model. So the torus action given by some matrix A and the log linear model MA for that same matrix A. Okay, great. So the next connection that I promised to tell you about is the one between polytopes and invariant theory. So now we have group G that acts linearly on some space V. That is, we associate each group element a linear transformation on the space V. Okay, so then we can recall these definitions that the orbit is the set of points that we can reach, starting at V by multiplying by some group element G, and the stabilizer is the group elements that fix a certain point V. Okay, so these definitions are standard. Maybe this one is also standard, but a bit less standard. So the capacity of a point V is defined to be the infimum of its distance squared to the origin as we range over the orbit. Okay, so this is the picture of the setup. So we have some space that our orbit lies in. So for us, this will be a complex vector space. Now we have our point V, and we can take its orbit under the group G. So this is our orbit. Now, as we range over the orbit, we're looking for the closest distance that we get to the origin. So in this case, the closest that we get to the origin is achieved at this point here. And then this distance between the origin and this point, or more specifically, this distance squared, is our capacity. And it's the capacity of that point V. All right, so there are then ways that we can categorize points V according to properties of their orbits. So specifically according to the properties of the capacity. So we say that a point is unstable if the capacity is 0. So if the closest that we can reach to the origin is actually distance 0, or the infimum is 0. The opposite of unstable is semi-stable. So a point is semi-stable if the capacity is strictly positive. A point is polystable if the point V is non-zero and its orbit is closed. So we can check why polystable is a further restriction on semi-stable. And finally, a point is stable if not only is it polystable, but its stabilizer is finite. All right, so these definitions are from geometric invariant theory, where they arise in the context of constructing moduli spaces. And they're usually defined in more algebraic terms as the vanishing or non-vanishing of certain invariants, but those that algebraic characterization is equivalent to this more topological characterization in terms of this capacity function and where our orbit lies in relation to it. Okay, so yeah, if you haven't seen these definitions before, then you can wonder what happens. Which points are unstable, semi-stable, polystable, or stable for the example of a finite group, or for the example of GLM acting on vectors in CM by left multiplication, or maybe for a first non-trivial example, or a first example where you actually see these intermediate notions appearing. We can consider the action of SLM1 times SLM2 on the space of rectangular matrices, M1 by M2 matrices by left-right multiplication. So certain matrices will be unstable, certain will be semi-stable, and so on.
Can I ask just a background question?
Yes, sure.
Yeah, so can you just say a little bit about why these definitions are called like why they're called unstable, semi-stable, polystable, and what you're looking for, like what do you consider to be a good property?
Yeah, thanks. That's a that's a great question. So maybe the first thing to say is that the unstable points is the set or variety called the null cone, which is the variety of points where all invariants vanish. So this is the variety of points studied by Hilbert, and you can ask questions like for which type of groups is the null cone finitely generated, and so on. And that's what he was working on with Hilbert's basis theorem and everything like that. So, okay, so the unstable points are very interesting, especially from this classical invariant theory perspective, but they are interesting because they're a bit pathological. So having 0 in the orbit closure means it's very difficult to distinguish that point from 0. You can't evaluate invariance on that point to distinguish them from 0, because every invariant will be 0 there. So the ideal situation when you have invariance and a group action is to be able to distinguish points according to the values that their invariants take. So we'd like to be able to decide, given 2 points, are they in the same orbit or not? Well, we can just evaluate our invariants at those 2 points and see if they give the same list of numbers, yes or no. And if the ring of invariance is finitely generated, then this will be actually a finite list. So we can just evaluate this finite list. And if all the numbers are the same, then we'd like to say that these 2 points are in the same orbit. But this only works up to closure. So that's why we have these closeness conditions coming in. So we can think of the properties of a point as getting better and better as we go down this list. So the best situation is that we're dealing with a stable point. And the most difficult situation is that we're dealing with an unstable point. And in the context of moduli spaces, the unstable points are those that we at which our quotient map is not defined, and the stable points, this is if we restrict to the stable locus, then we get a nice orbit space with lots of good properties holding. Yes, hopefully that was helpful.
Perfect, thank you.
Yeah, thanks for the question. Are there any other questions? Okay, great. So let's see what all of this looks like for our torus action. So our action was given by this matrix of integers. And I'd like to, so before I define the polytope P of A to be the convex hull of the columns of the matrix A, I'd now like to define a modification or a subpolytope of P of A called Px of A. So this is the convex hull of the columns of A indexed by some j that lies in the support of our vector x. So Px of A only notices the columns of A that are in the support of our vector x. So whenever x has full support, this Px of A is just the same as our original P of A, the convex hull of all the columns. If x is 0, then it's empty, and in between we get various subpolytopes. All right, so then the Hilbert-Mumford criterion applies to such a torus action to give us the following characterization of these notions of stability. So we consider the torus action of our group given by our matrix A with linearization B. Okay, then a point is unstable if and only if this vector B is not in Px of A. Okay, so what's missing here is the stability of the point is the stability of the point X. Okay, which over here we call V, but it's okay. There's stability this is the description of, this is the characterization when X is unstable. So if B is not in the polytope Px of A, then X is unstable under this group action. If B is in the polytope Px of A, then X is semi-stable. Okay, polystable. This is when B is in the relative interior of this polytope, and stable means that B lies in the interior of this polytope. Okay, so int P is interior and rel int P is relative interior. Okay, so this isn't the usual statement of the Hilbert-Mumford criterion. It's usually given in terms of one parameter subgroups, but this is a consequence of the usual Hilbert-Mumford criterion in the context of these torus actions. Okay, so this is our connection between polytopes and invariant theory. So here are the invariant theory notions of stability, and here they have been translated into saying something about polytopes. And I've just spoken about torus actions here, but this connection also holds for more general group actions. So this polytope here is maybe the first example of a moment polytope, and these can also be defined for more general group actions. Okay, great. So this, on the previous slide, we saw connections between polytopes and these notions of stability. I'd now like to zoom in a bit more on connections between polytopes and the null cone. So, okay, so we have a group G acting on the space V, and the ring of invariance is the ring of polynomial functions of V that are invariant under the group G. Okay, so yeah, I mentioned before that Hilbert studied these in the late 19th century, and this was the setting for Hilbert's basis theorem. So for the torus action given by the matrix A with linearization B, a point being unstable means B is not in this polytope Px of A. So that's what I said on the previous slide. So this means we can describe what the irreducible components of the null cone look like. So they will be various linear spaces, since the membership or non-membership of a point in the null cone only depends on its support. So we'll get various linear spaces, and the linear spaces we get are indexed by sets J such that the polytope Pj of A is maximal in P of A, but not containing the vector B. Okay, so here's the picture that I showed early on. Here we have the same matrix A and different choices of linearization vector B. And we can see as B moves around what the irreducible components of the null cone look like. So let's see, to take this example, the irreducible components are the linear spaces on index sets 1, 2, 4. So that's this maximal subpolytope, 1, 2, 3. That's this one, and then 3, 4 is that one. So our polytope picture also tells us finer information about the null cone, tells us what the irreducible components look like. And it tells us polynomial equations or monomials that must hold for a point to be in the null cone. So some x is in the null cone if and only if all of these products vanish, where our index set J gives some subpolytope Pj of A that's minimal in P of A containing the vector B. So this is sort of the opposite condition. So now we have this our same polytope and our same vector B. So now these give the monomials that we need to check to see if our point lies in the null cone. And the monomials we need to check are, in this case, 1, 3, 4. So this has to vanish. And 2, 3, 4 also has to vanish. Okay, so that's polytopes and the null code. All right, so now we can get to connections between invariant theory and statistics. So yeah, as I mentioned before, this is something that we've been working on recently. The goal is to connect these two pictures that I've been talking about. So on the invariant theory side, we have a point and its orbit, and we're looking for its closest distance to the origin. And on the statistics side, we have our space and we have a model and some data, and we're looking for the point in the model that best explains the observed data. Okay, and then more specifically, on the invariant theory side, we have these notions of stability that we've seen. And on the statistical side, we have these properties of the likelihood function. So what can happen as we try to maximize our likelihood function in order to find the MLE? Well, the first possibility is that the likelihood is unbounded from above. This is the worst case scenario. Slightly better, the likelihood could be bounded from above. Even better, it could attain its bound. So that is, the MLE could exist. And the best case scenario is that the MLE exists uniquely. Okay, so we have these four notions of stability over here and these four properties of the likelihood function over here. And the goal is to connect these pictures by connecting these properties. Okay, and so we've been looking at this problem in various different settings. So today I'm talking about this toric setting with log linear models. So that's this first paper here. We've also looked at it for multivariate Gaussian models and also in follow-up work with Visu Makam and Philipp Reichenbach for Gaussian graphical models. Okay, but today I'm talking about the toric case where we're dealing with log linear models. So what does this correspondence look like for toric invariant theory on this side and log linear models on this side? Okay, well, we can relate stability to existence of the MLE. So we have our invariant theory picture here, and we have our torus action given by some matrix A. And then on the statistics side, we have a log linear model M sub A, where A is some matrix. Okay, and this is what the correspondence looks like in this case. So unstable and stable do not happen. And polystability tells us exactly when the MLE exists and is unique. And in the semi-stable case, the MLE does not exist. And we can define something called the extended MLE in that case, which allows us to lie on the boundary. And this is unique. So this distinction between semi-stability and polystability is telling us whether the MLE exists or does not exist. All right, and here are the terms and conditions of our theorem. So this is our matrix. It must have the all ones vector in its row span. And this, then we have some data vector whose entries sum up to n. And then the stability is the stability of our complex torus. And the action is given by the matrix n times A with linearization B. So these are the conditions under which this correspondence holds. Okay, and the proof idea is to combine what I've been telling you about so far. So we have these polyhedral conditions for the MLE existence from this 2006 paper. And then on the other hand, we have the Hilbert-Mumford criterion, and both of these tell us something, recharacterize both of these problems, the left-hand one and the right-hand one, in terms of a particular polytope and the membership of some point in that polytope. We can match everything up, and all of these choices enable us these two settings to match. Okay, all right. So this this correspondence tells us about how difficult this optimization problem is and how difficult this optimization problem is. So does the MLE exist or not? And is the orbit closed or not? But we can also hope to use this optimization problem to give us a solution to this one, and maybe vice versa. So can we use this connection to the group setting to actually find the MLE? Well, the Kempfness theorem says that in this special case of a torus action, the Kempfness theorem specializes to say that the closest distance to 0 on an orbit closure is attained at some vector x that satisfies this equation. So NaX to the 2 equals the norm of x squared times A of u, where x to the 2 is the vector whose jth entry is mod xj squared. Okay, so this this statement here specializes the vanishing of the moment map to the setting of our particular group action of interest. Okay, and this this equation here enables us to obtain a theorem that the MLE given u for our model is this vector x to the 2 divided by the norm of x squared. So this says that we can get the MLE from our point x of minimal norm in the orbit, and it tells us what to do to that vector x to obtain the MLE. And this operation, I mean, x is a vector of complex numbers. So we would like to obtain something consisting of real numbers that sum up to 1. So this, we can check that this is a vector of real numbers that sum up to 1. So that's good, because it should be a probability mass function. Okay, so how can we show that this is the MLE? Well, before we saw Birch's theorem, which characterized the MLE in terms of this equation here. And we can check that if we let p hat be this, then this equation is the same as this one. So we're already very close to showing that this is the MLE. We have that it satisfies the right equation, but we need to show that this point is actually in the model. So this is the challenging part. A point, an MLE has to satisfy this matching of sufficient statistics, but it also has to actually be a point in the model of interest. And to show that the point is in the model, we can use the implicit description of this model. So these vanishing equations for its Zariski closure. Okay, so finally, I'd like to mention some similarities and differences between algorithms on these two different sides. So on the invariant theory side, we have this problem of norm minimization on a complex torus orbit. And on the statistical side, we have the problem of maximum likelihood estimation in a log linear model. And algorithms exist for solving both of these problems, but we can now say that these problems are very closely related. So whenever we've solved this problem, it actually already gives us a solution to this problem. All we have to do is take our x and compute this x to the 2 divided by norm of x squared. Okay, so in practice, how do we actually find this optimal point? Well, on the side of maximum likelihood estimation, we saw in the independence model that we could just use this formula. But more generally, we need to use some iterative method. So what is typically done is iterative proportional scaling. So we want to iteratively update our vector p until we approximately match the sufficient statistics to the data. And this is what the update step looks like. Okay, so don't worry too much about this, but it's doing some update such that we remain in the model and we get closer to our vector of sufficient statistics. So we have a certain product of entries of the data and the previous iterate raised to some power times the previous iterate. And there's one parameter in this update step that can vary, and that's this alpha here. And it's an open problem in algebraic statistics to study these iterative updates for various different alpha and to understand which alpha leads to the best convergence rate of these iterates. Okay, and then on the norm minimization side, this is given by a convex optimization problem. So we're computing the capacity of a vector of full support. So we can rewrite this as this infimum over a group orbit. Our orbit has this very nice structure, so we can actually expand everything in terms of the matrix A and the vector B. And then change of coordinates leads us to this form where we're minimizing a sum of exponentials where the sum is given by these EJ minus B vectors. Okay, so there are different algorithms used on different sides and maybe better understanding of each, or more specifically in this case, having a good understanding of this norm minimization problem could maybe tell us something about this iterative proportional scaling setting. All right, and yeah, that's all I want to say. Thanks a lot.
Thank you very much, Anna, for a very nice talk. Let's thank you. Do you have any questions? Maybe before asking some question, I would like to ask something briefly. So you have this picture. You always use this simplex with some kind of curve inside, which is given in your toy example by the determinant of this matrix to vanish on some kind of quadratic or some other polynomial condition. Do you have any kind of generalization of this model where which goes towards more the direction of a Grassmannian statistic kind of model? So where you have maybe Plucker relations instead of representing these quadratics, or something which goes more in that direction. And also, this is my first question. The second is, you show these two models, sorry, these parallels between the invariant theory of a specific type of group action in a vector space, and then the other log linear model on the other side. So does this generalize to more to other examples, or is there a more general framework that you can always connect, or is specifically tied to what you just said? And in relation also to maybe generalizing to Grassmannians or Torus action in the Grassmannian, or these kind of examples.
Yeah, thanks a lot for the great questions. So, okay, so firstly, to answer your question, what types of models are we looking at? So here I mentioned that the implicit description of the log linear model MA is always given by these binomials. So the equations are that Q to the V equals Q to the W whenever AV equals AW. So this is the this generalizes the determinant equals 0 equation from the toy example to something more complicated, depending on a general matrix A. But this is not a Plucker relation. So to answer your first point, I don't know. I think it's yeah, it's possible to consider a class of models that that are defined by the vanishing of certain Plucker relations. I think that the goal is to or a prerequisite is to have this group action that's closely associated to the model, and to then see that group action appearing in the log likelihood function. Yeah, I think that would definitely be something interesting to think about. In terms of the generality with which we know about this correspondence, so yeah, today I was talking about this this setting of a discrete statistical model, so one with finitely many states, and then focusing there on log linear models and on toric invariant theory. What we don't know is how, in this discrete setting, how or whether we can extend beyond log linear models to something where the invariant theory is also more complicated. But we know about this correspondence in much greater generality when dealing with multivariate Gaussian models instead of discrete models. So yeah, so that's this second paper here. So we have a sort of branching of the two settings in which we've studied this problem. There's this discrete setting, and then there's the multivariate Gaussian setting. And yeah, another thing we don't know is how to find a framework in which both of these sit as examples.
And same. Okay. Yeah. Thank you.
Thanks. Yeah, thanks.
That's very useful. Sorry. Now, do you have questions for Anna?
I have a question. Hi, Anna. It's Simon.
Oh, hi, Simon.
Thanks for the nice talk. So you've assumed throughout that the vector 1, 1, 1 is in the row space of A. But so if it's, suppose this is not the case, are you aware of any variant of this scaling algorithm that still works?
Yes. Okay. Good question. So I assume this all ones vector is in the row span of A. So this ends up being important in various different ways. It's a typical assumption on the statistical side. It ensures that the uniform distribution is in the statistical model and that you're dealing with a discrete exponential family and so on. So it places nice sort of natural statistical restrictions, but it also makes things work out nicer on the invariant theory side. So in particular, the all ones vector being in the span of the matrix A is what prevents this stable case from happening. So that leads to this distinction between semi-stable and polystable, because our polytope P of A then lies in a hyperplane, the hyperplane given by the all ones vector. And since the polytope lies in a hyperplane, nothing can lie in its strict interior. So that gets rid of this stable. So, okay, this is not answering your question. This is just giving some background on the assumption that the all ones vector is in the row span of A. Can we extend iterative proportional scaling? So these updates when it doesn't. I don't know. So so this is something that we were looking at a bit, because you can modify the matrix A. Yeah, this is something that we looked at a bit in the paper. So there's various convergence results are known about iterative proportional scaling with various conditions on the matrix A. So for instance, there's the stronger condition that the row sums of the matrix are actually equal. So this is stronger than the condition that the all ones vector is in the row span, because it says that the way you get the all ones vector, or like the all A's vector, let's say, is actually just by summing the columns. So you can make this work by adding on extra rows to the matrix A and showing that this doesn't change the model. So I wonder if something similar could be done for the all ones vector assumption. Yeah, I don't know.
No, thanks. I was wondering, because I've been looking at this in the context of linear programming or minimizing entropy functions on a polytope or on an unbounded polyhedron. And in that case, you don't have this vector. And I was trying to adapt this algorithm, but didn't succeed so far. So thanks.
Yeah. And in case there's any people on the physics side who are listening, also to mention that that Simon and Bernd have some work that relates maximum likelihood estimation to the scattering potential. I mean, you can say, yeah, so send him a message if you're interested in how this implements the scattering potential.
Yeah, thanks, Anna. Please do.
And so is there a connection with the invariant theory in that sense, or?
Off the top of my head, no, not that I know.
Okay.
Definitely.
I see. Okay, thank you. Are there more questions from the audience? Okay, so if not, let's thank Anna again for a nice talk.
Thanks.
Thank you very much. And so it was nice to have you here, and see you next week for the next talk. Thank you very much. Bye, Anna. Bye, everyone.
Bye, everyone.
Bye.